Okay, Yufan, please go on.
Do I need to show? Oh, I think no need.
Mm.
Hi everyone, I'm Yufan. Today we will talk about Codebert. It is a pre-trained model for programming and natural language. This paper was published on EMNLP 2020. There are 9 others. The main author is Feng. He is a PhD author in Harbin Institute of Technology in China. The work was done in Microsoft Asia Research.
Let me see the other professor. There's some. They're all students, right? Oh, there's.
No, there are nine others. Two is student. They are student.
Okay, the third one is a postdoc. Postdoc is a postdoc. Uh, and let me see the rest authors. Zhong.
Yes, some are professor in HIT,
Mm.
Harbin Institute of Technology. Some are partners of Microsoft Asia.
Okay. I think I do not know the professors in HIT now too much. Okay.
Yeah. So we first have an introduce of language. Language is made of discrete structure sequence of symbols with the syntax structure of sentence captured in a tree. Neural net models operate on continuous data. They translate the symbol information into vectors in high dimension space called word embedding. For example, the distance between queen and king should be equal to the distance between the woman and man. And the vector of woman should be closer to the king than queen, to the queen than king. Okay, after we understand what is the word embedding, we can go further about how to achieve these word embeddings. I will first introduce the background. First is the pre-trained model BERT. A large pre-trained model have dramatically improved the state of art on many NLP tasks. They are trained unsupervised on a large corpus and learning contextual representation from text, and then fine-tuning on some specific data set of some specific tasks, and then they show great performance. The BERT model is one of the pre-trained model. Here we take the most important mechanism, mask language modeling for further discussion. If we want to pre-train the language on this example, Alaska is about 12 times larger than New York. We have 2 approaches. The first is autoaggressive approach. That means left to right prediction or right to left prediction. The second is masked language approach. It uses prediction of a word using all other words in a sentence. The words that predict that is in red, in BERT case is masked out, replaced with a specific token or a random vector. We typically mask some word in a sentence and have the model predict those masked words with other words in sentence. By training the model with such an objective, it can essentially learn certain statistic properties of word sequence.
Yeah, by the way, Yufan, so giving the masking language modeling, I mean the language masking task or the left to right or the right to left prediction. So do you consider they're the same tasks or the separate tasks?
Do you mean
So do you think the word prediction task is almost the same with the language masking or word masking tasks? So because when we train the BERT models,
same?
they're separate tasks, right? Hello?
What is separate task?
I mean the different task, the word prediction task and word the word masking task. They're
They are the same task
you
actually.
think so you think there's okay, so you just pick up different words to predict another. The only difference is they choosing different world surrounding the target world. Okay.
So
Okay. So in this case, okay, the difference is that the sampling, right? The only difference is the sampling. Sampling means a sample used to train a model.
I don't think so. The difference is that when for this task, this is not masked language modeling. For this word prediction, it's just left to right prediction. That means when you predict, yes.
I got it. So when I design a model, I'm thinking about when the model architecture. So when we design a model architecture,
Yeah.
we're supposed to have multiple words inside, right? And suppose it's a black box models, and it will output some tokens or vectors here.
Yeah.
Right. So in this case, what for the word prediction task and the word masking task, so they share the same input. The input share the same shape. Same shape. The input shape. The input shape is exactly the same.
That's the sequence. Yeah.
Yeah. Okay. So the only difference is that they may sample. So we can consider this as these three words is the context. So the only difference is that we just fit into different contexts use different contexts as the input, and using the target word as output.
Yeah.
Right? And if it's for a masking task, maybe there's another REST word, but we just just use another or using another different context.
Oh, the architecture is different.
Oh, okay. So yeah, that's what I asking. So that's definitely what I'm asking. So
I'm sorry, I just misunderstand this.
okay, so anyway, so maybe I haven't make myself well understood. So now we can come to the question is that if the architecture is different, so the BERT model have to be trained on different tasks, or maybe connect with different architecture.
The BERT model will be trained on different architecture.
Anyway, BERT model is going to, for example, this is the BERT model, right?
Yeah.
And it will output a vector. So this is embedding. This is embeddings, and this embeddings will fit into different, maybe fit into different tasks.
Yeah.
So this is the model one for maybe the word prediction, and this is the model two for the word tasking, right? So that means this BERT this BERT model or embedding model have to be connected to multiple architecture to train performance.
Oh no, because you first pre-train on a large corpus, then you get the word embedding. Then this word embedding can be used for other.
No, I'm just asking for when we training the word embeddings. If we want to train the word embeddings, we have to train the word embedding with a specific task.
No. It's a self-supervised method.
Self-supervised method.
Yeah.
Yeah. So okay. So will you please clarify? So when we train the models, and anyway, we need to design a loss functions and how the loss functions and
Yeah.
we do not need a specific formula. We just need a intuition of the loss. So how do we?
So this is the model architecture picture. You can see the input is a sentence. Oh, this is the two sentence. My dog is cute and he likes playing. This is two sentence, and the clause is the sign of the start of the sentence, and it also can be learned as the meaning of the sentence. So this is the input. So what is the output? The output is that is just a new embedding. So it is an iterative process. Could you understand? So
no. So here's output vectors. When if we want to train the models, the output vectors have to be connected with some or involved into some loss calculation, right?
Yeah, the loss is like the dog. If you mask the dog, then the label.
Yeah. So I think that's exactly what I mean. So So this task, so if the output is so this model will output a dog. So that's what I mean. So giving embeddings, we embed everything here, and this model is going to predict the dog. And based on this output, we update the values in the BERT model for learn how we embed a word.
Oh,
But
And
then,
also my point is that
oh,
now this is the example raised in these slides is the masking task, right? So we mask a dog and we're going to predict dog. And in next, and also we can use another task, design another task to learn embeddings. So they're supposed to be many tasks as long as they can learn a good embeddings, and that is fine. Is there any
there's
confusion there?
many methods to learn embeddings. The
Mm.
mask language model is one of them.
Yeah, so we are talking about a mask. So so your point is that we only connect the embedding with one task.
When pre-training, this is only the BERT is using the master language modeling as the pre-training methods.
But of course we can use some other tasks to do the pre-training. And all what I talking about is about pre-training. And this process is all about the pre-training task.
Yeah, pre-training task, you can say you can use different tasks. In this PPT, you can just use mask language modeling.
Yeah. So when you are raising these two slides and think about it, do we need to interchangeably change the task to make sure the BERT model or the learning embeddings can be well fit to both tasks?
sorry, I have a confusion here because my understanding is that the BERT model will not be updated.
No, the BERT model will be updated. So here we're talking about how to learn a BERT model.
How to learn a BERT model?
Yeah. So anyway, so we will find a way of encoding a high dimensional vector. So by right, we're supposed to be a one hot vector for dog, right? Suppose we have 1,000 word in vocabulary, or 10,000 word in vocabulary, so supposed to be a vector of 10,000 dimensions. So the value the value of BERT model is got to reduce similar to Shannon reduce, but it's kind of very different in terms of semantic point of view. So
I think BERT is just some kind of input transformation.
Yeah, definitely.
So you don't update the weight parameters in BERT.
But the point is that how do we learn the BERT?
The BERT is pre-trained on other data sets, on other large corpus.
Yes, we are talking about
so
how
we just adopt the weight.
Yeah, I understand. But we're talking about how the BERT is pre-trained on the other data set.
Oh.
And this is the data set of we're pre-training BERT.
There's two questions. The first is how we pre-train the BERT. Actually, the initial word embedding is randomly one hot vector. Maybe you set 200 dimensions, then you have a 2-dimension 0 and 1 vector. And for every iteration, the word embedding, sentence embedding, and the position embedding would concatenate and as the input of the neural network, and the neural network, and then predict the mass, predicts the mass work dog. In that process, the weight is updated, and you get a new output. You get a new embedding of the word. So you just use the new word embedding as the input of second iteration. So during every iteration, the word embedding vector is changed. And then finally you get a final word embedding. This is how BERT worked. How BERT gets the word embedding.
So let me rephrase. For example, let's suppose that the predefined dimensions, the predefined number dimensions for the embedded word is maybe three dimensions. So suppose the dog means 0.8, 0.2, and 0.5. But of course during the pre-trainings, and the value here will be changed.
Yeah.
And right. So anyway, we have model architectures. we project, for example, 10,000 dimensions into these 3 dimensions. And these 3 dimensions will be used for another task to predict the dog. So whatever the word my is cute, etc., will always be projected into an embedding vector. And all these projected embeddings, despite they are not necessarily accurate, will be feeding to the models. This model is more like this model will usually be the transformer or area stem, whatever, and then it's going to output another vector, and this vector is supposed to be has a similar value to the dog.
The final output should be a likelihood, right?
Should be, I think it should be a vector, right? There should be a vector.
Should be likelihood, I think. Should be a vector of likelihood.
The vector of likelihood, you mean?
Yeah, so each entry is the probability that this position is a specific word. Then the vector length is just the number of words in the dictionary. And then you want to maximize the likelihood where the ground truth is just that word.
So that's the details of design, the laws. Hey, Yufan, are you following the discussion?
Yeah.
Yeah. So I'm asking the loss function. So so there are 2 different explanations. So Ruofan saying that the output will be a softmax. So softmax is the likelihood Ruofan mentioned. So giving suppose we have 10,000 words in vocabulary, so the final output is supposed to be a dog. The dog should be a probability which is showing that the probability of dog will be the highest. And another explanation, so that's my speculation, is that we still output another embedded vector, and this embedded vector is supposed to be the same with the dog. So which one it is?
I think your view is close to the bird, because if you said it's 200 dimension, the whole world is 200 dimension. Regardless of the.
You mean 200 here? The 200 means the number, the size of vocabulary.
No.
Oh, so it's the size of the embedded vector.
Regardless of the size of the vocabulary, no matter the size of the vocabulary, it's all 200 words.
Okay, 200. Okay, the 200 dimension of the embedded vector.
Yeah.
Okay.
So it just puts the words to a 200 dimension space.
I think Ruofan is correct.
Yeah, I think mine is correct.
Because the bird model will output the embedding, right? And when it is connected to a downstream task like word prediction, then the embedding outputted from the bird will be used to do a classification task.
Yeah.
Yeah.
So finally, the output was supposed to be the vector is the size or the vector of size of vocabulary size.
I think it's vocab size.
Vocabulary size. Okay.
Yeah.
Okay. Thanks for the clarifications. But finally, so maybe I'm going to read the last question.
Wait for a moment.
Okay.
So why is it vocabulary size?
Because you want to predict what is the most probable word for this position, right?
Probable word for the you mean for the.
So given the context of my is cute, he, and you want to predict what is the word at the position 2, right? So if the model is correct, you expect to have dog at this position. So you want to maximize the predicted likelihood of having a dog at this position.
So why is a vocabulary size?
Because I will have different probability for different word.
Yeah, I think that it does not predict the probability. It shows the position of the word in a 200 dimension space.
Then how do you design the loss?
The loss is designed as the output vector and the original vector, the similarity.
The question here is that do we use one hot vector or using the embedded vector? So that's a difference. Definitely we know that we will output a vector representing dog, but this vectors is 200 is of the size of 200. The 200 is the embedding size, or 10,000. It is the vocabulary size. So that's the questions. So my first guess is about the embedding size, but Ruofan and Yihao saying that it's about vocabulary size.
I think our difference is that I think the BERT is not predicts the probability of the not the likelihood, but predicts the
exact embedding vector.
Yeah, embedding.
So I think either could be either case could be fine. It depends on depending on the experimental results. So, but if it is the embedding size, suppose let's say that if the output will predict a vector of the embedding size, so we somehow need to back project the embedding vector to dog, right?
Yeah.
And assume that there must be a way to using the BERT model to revert it back. Is that possible? So suppose it would output a dog, but it's supposed to be okay, right? So may not necessary to think about it. I think both would be fine. Both could be okay. But Yihao, based on what you read in the materials and the standard operations using the output is supposed to be a vector or vocabulary size.
Yeah.
So that's what you remember.
Yeah.
But
okay.
But if it is a dimension is the vocabulary size, that means every word has a very high dimension, and you.
No, I'm not talking about the output of downstream task. So here, BERT is just outputting the embedding. That's the embedding size output. And then when you pre-training on a task, you should connect to a task, a downstream task.
So here,
so the task here will output the likelihood.
This is definitely embedding size.
Yeah.
So we are talking about this vector.
Yes.
So what's the downstream?
Downstream task is about the word prediction, or the masked word prediction. It's called a downstream task.
Actually, when we do the pre-training of BERT, we actually have two tasks. One is the mask language, the MLM, just you mentioned, and the other one is the next sentence prediction.
Yeah.
I think you also read about this, right? So we have two separate tasks to do the pre-training.
And that's also what I mentioned, that they will connect to the BERT. Maybe this is called, so let's call this upstream task. So upstream task is more like encoding, or the encoding matrix, or encoding model. And this is about the prediction models. This is downstream task.
But I think this is not a downstream. The whole is a pre-trained model.
Definitely. Otherwise, there's no one to prediction. But we can replace this task. Just what you mentioned. This downstream can be the masked word prediction. Can also be the left to right word prediction. This can be replaced, right? This component can be replaced by a lot of the other tasks. But I think the most frequent or most popular task is about the masked word prediction.
Yeah.
Yeah. So let's come back to the question. So here, Yihao remember that this downstream task will output a vocabulary size, and this definitely will be embedding size. So I'm saying that this vector might also be a vector of the embedding size.
So if the downstream result is about based on the vocabulary size, so how to update the embedding vector?
Because yeah, you can use like cross entropy because you know the ground truth. You know the ground truth is dog, so you know that position is 1 and other position should be 0. So your softmax probability vector should be close to the 1 hot ground truth.
But I think this trick can also be applied on the embedding size.
So the embedding vector, you can't update. You always input the 0, 1, or 1 hot vector.
Embedding vector. I mean you mean the 1 hot vector, right?
I mean the 1 hot is ground truth, not the embedding vector.
So
embedding vector then.
How BERT works? You just use the ground truth 0 or 1 hot vectors. Then finally the BERT get a new word embedding.
Yeah. So we want to train the word embedding.
Yeah, this is to be trained. Everything.
This is to be trained.
So you means the BERT is not training the weight, it's just training the embedding.
Yeah, we're talking about we're talking about the pre-training, the pre-training process. So we are training how to embed a 1 hot vector into embedding vector. And when we got these embedding vectors, we need to feed this embedding vector into a downstream task and make the predictions. And these embeddings were supposed to support the downstream prediction tasks. And of course, there's a lot of the work that different tasks may have different kind of embeddings. So usually many tasks is that to learn the embeddings and the task together. That is I think that's a very popular task here, especially for the program. Sometimes the Python code, the Java code will be they're not supposed to be a generalized embeddings for any programs. For example, if for debugging, for testing, for code generations, for comment generations, maybe the different tokens play a different role in different tasks. By this means, we may need to learn the embedding together with the task.
Okay, I will fill the survey on
survey a little bit. So I think we have already lingered on this point too much. Let's keep going on.
Okay. So after we talk about the masked language approach and the BERT architecture, we have a short discussion on why BERT works. It is a very difficult question as neural network is always hard to explain. Here I just show some of my understanding, mostly refer from these 2 papers. They analyze the result of the embedding and try to give some hints behind the BERT. The first is it can encode semantic features in its embedding. Here is an example. Considering here is the example. You can visualize the embedding for words like die in different sentence contexts. We can see that the word stance affects the embeddings. You can see that some German article die is just far away from the single person die in English. Okay, and the single person die and the multiple people die is also different in space. They are far away in space.
So this is a visualized. If each point is a token, right? Each point is a word.
Yeah,
each point there is a word. So it also project from the embedding vector into a 2-dimensional visualized space.
Yeah. So you can see that the different sense of a word are separated, and the word sense is accomplished by this separation.
So your point is that the word in different contexts may have different vector presentation.
Yeah. So I think it is not a one hot true answer. You mean you can understand? It's different. It's for different words in different sentences. They are also different. Or for one word in different sentence, the output is different.
Could you isn't here trying to visualize the sentence embedding instead of one single word embedding?
No, It's just input one sentence and output the die vector. Die.
I think it's sentence embedding, right? It's not the one word embedding.
It's a word embedding. You just input the sentence to the BERT.
To the model, to the BERT model.
Yeah.
And the BERT, then the BERT model will output a sequence of embedded vectors.
Yeah.
And we will find that suppose we're using the same word die, and this word die will have very different embedding permutations, giving
Different.
regarding its positions or regarding its usage in different sentences. So your point that a BERT can taking the context information into consideration and generate very different generate very different presentations.
So
Okay.
So in different sentence, the same word have different meaning. So the BERT can catch this information. So the question we just asked. So I think this is not just the one hot. Okay. So
because here we are just trying to do some visualization, so it's not exactly what is the model is trained. Because I share a screenshot in the chat, you can check that it's trying to maximize the likelihood, not trying to look at the embedding.
Okay.
Yeah,
okay.
but the point is that if because when Yihao once gave a report, but that was an individual report saying that suppose there's the word bank. The bank can either means there's the commercial and financial institute, or it's just at the side of the river, right? So in that case, if we were like maybe it can still work even if we didn't want hard vectors. But my intuition or my first guess is that the final output can be embedded vectors. Can be because it is still work. It's at least it's technically feasible, right? But we still need to do the survey and have a second check, and maybe their both approach is feasible depending on what is the goal we're going to use to achieve, right?
Okay. For the second picture, we can see that within cluster there seems to be there are many separation of finder shapes of meaning, like the word line. For different meaning, it also have different cluster. That means if the line in different in some sentence they have the same meaning, they can be a cluster. They can get closer. Could you understand this?
Yeah, definitely. That's the same examples. This example show the same meaning of previous ones.
Yeah, this is different. If the word in one sentence is different meaning, so they will be far away. If a word in the some they have the similar meaning.
So I suggest here that in the previous slides, you should draw a background. You should draw a background like the second one. So will you please go back to the 11th slide?
Okay.
So here you should think that this is a canvas, and these data are clustered here, and this part of points are clustered here, and these points are clustered here. So in the space, we will find that the world giving the same context, their embeddings can be grouped, will be clustered into, will be grouped into 3 clusters, right? So it's better to have a canvas or background for people to get a better understanding.
Yeah.
Right. Okay, keep going on.
For the third picture, we can see that the BERT encoded in the vector output for a sentence is geometrically approximately copies of syntax trees. The syntax tree is one of the language model. That means the BERT actually captures the features of our traditional language model. Words in a sentence are given locations in a highly dimension space, and if we subject this word vector to a specific transformation, the the distance between these locations maps to a syntax tree distance. This means we can recover the syntax tree and the dependency tree too with directional edges for a sentence by transforming the word vectors using a transformation, and then find a spanning tree on the distance between the word vectors. So that means the BERT also captures some features which is used in traditional language model.
So let me. So may I ask so there's the minimum spanning tree, right?
Yeah.
So that means that if we giving the vectors in the embedded space,
yeah,
and we can if we construct the minimum spanning tree, it almost like a syntax tree,
yeah.
and here
so that means it is useful and
I understand it's meaningful. It's meaningful, but usually the bird is means the semantic distance, right? So given a word like the queen and a king, boy and a girl, so
Yeah.
it's more a semantic equivalence. And how the semantic distance be applied in a syntax? The syntax is more like the structure connection, right? The syntax tree is more provide a structure information, for example, out and off, and why there will be a link between on and off.
Because first the birds have different representation. You can just think that for different iteration, it will output different representation of the word. For the second point, if you input one sentence, the bird will extract the structure information from this sentence.
So
So
here
that means
for giving that the word in different sentence will have different embeddings. So in this case, how can we use BERT to predict the vectors?
pardon, please.
So here I'm asking that giving a sentence here, right?
Yeah.
Give a sentence here, and suppose we need to interpret each token into an embedded vector. And so the input of BERT is not only a token, but also its context. Am I right?
Yeah.
So, but for now, for example, if we want to translate the into embedded vectors, and how can this input the BERT? It just put it uses one hot vector into the BERT model, and how do we present its context? How do we represent this context?
You mean you didn't have a sentence, you just have a word the?
I think the same. For example, if we also would like to, if we would also suppose this is the context, chef who ran, whatever it is. But if we want the embedding of chef, we still need its surrounding context. And that will almost cause us a recursive problem. Have I made myself understood?
If you just have a word, you just input a word. If you have a sentence, you just input a sentence. I don't understand your question, actually. So if you just want to get the word embedding the, you just input the to the BERT. If you have a sentence, you want to get the sentence, you get the word in the sentence meaning. So
but the problem is that if the word is in different, the same word in different contexts or in different sentence will have different embedding will have different embedded vectors.
Yeah.
And that means the context of the word matters.
Yeah.
And
so
the bird and for the bird and Yihao, you can complement if I'm incorrect. So and what is the so this BERT model only taking the one hot vector only and how many inputs does the BERT model take one hot vectors or a series or a lines or a sequence of the one hot vectors?
a series or lines.
A sequence of the one hot vectors. A sequence of one hot vectors. So given the BERT models, of course, we know that giving one token. So by right, giving the input of the BERT supposed to be one hot vector, right? And then we will input this embedded vector. This is one hot vector. Am I right?
Yeah.
Mm.
And my question is that giving its embeddings depends on its context, right? So as I assume that when we use a model to predict its embedded vectors, it will not only take the one hot vector, it will not only take this one hot vector, will not only take its one hot vector, but also taking its context into the BERT model. Am I right? Or not?
Yeah, right.
It's right? So now here comes the question is that the input of these contexts are all one hot vector.
Yeah.
Mm.
Because you
so
originally have a dictionary. You have a dictionary like if you have the original one hot vector is here.
Mm.
So this is a BERT dictionary. So when you see another, all the words should be in this dictionary. If it is, if the word is new or created by programmer, then the BERT will regard this as unknown. It has a
no problem. So suppose we got a sequence. So the input of BERT is a sentence instead of an individual word. So the BERT will take a series of one hot vectors into its input. And also we need to, am I right? So or something I have some misunderstood here. Let me rewrite. So here, so suppose here's suppose it's a one hot v1. So this v1, v2 are all the one hot vector, v3, etc. That's vn, and this sequence of vectors will construct a sentence, and we then this sequence feed into BERT, and the BERT will output a sequence of the embedded vectors.
Yeah.
Okay. So the BERT is on the processing the sentence instead of an individual word. So giving the different combination of one hot vectors, and their embeddings were different. Hello?
Yeah.
Okay.
Yeah. That's why I'm asking whether the visualization is for a sentence or individual word. That's my confusion.
But I think the visualization is by taking the individual word in the space.
But if you take the individual word and your model is freezed now, so you will definitely output the same embedding.
No, maybe different because the die here, for example, it includes the German article die or the single person dies, and the BERT model will return different sequence of the embedded vectors.
So the embedded vector is for the sentence, not for the die. Yeah.
But we can infer the embedded vectors from the embedded sentence, because embedded sentence, the embedded sentence is actually a sequence of embedded vector.
Yeah.
And maybe that die will conform this word die will conform into one embedded vectors, and so does these dies, and the positions, or anyway, these two vectors will look very different, given they are in different sentences.
Yeah. So the
I don't know.
A sentence, and the output will be a sentence, a sequence of vector. You just check. You just choose the die vector.
Oh, okay. I understand. Yeah. Thank you.
Yeah. Okay. Keep it going on. So sorry, I actually, frankly, I'm not an expert. So when Yufan is giving, I will keep asking questions.
Okay.
So maybe one little question. The final question asking for slide 13. So you mentioned that the minimum spanning tree based on distance can correspond to the language syntax tree.
Yeah.
So for example, let me raise examples. So there's the word between ran and was, and the chip and was, right? So
what is run was? What's the
anyway? So because suppose this sentence is the chief who run to the store without a food, right?
Yeah.
So every pair of the word in this sentence will have a distance for their embedded vectors.
Yeah.
Right. But the minimum spanning tree will only select the, and also there's multiple minimum spanning tree, right? So giving a suppose each word will be a node, or is the point in the high dimensional space. So they have multiple versions of minimum spanning tree, right? But anyway, it's more like a, I think it's more like a,
I don't understand. For a certain sentence, it should have a certain syntax tree of sentence, and we find that the BERT can, the BERT word embedding can actually include the syntax tree.
Yeah, I understand it can include certain tree, and also what you're writing, what you present here is that we are using the minimum spanning tree to, anyway, so by right, all these nodes will construct a complete graph,
Yeah.
right? A complete graph. And we run a minimum spanning tree algorithm on the complete graph, and a lot of the edges, for example, the edge between random walls will be removed, right? And it's removed because it has a larger distance. Consider the distance between the chip and the walls.
Yeah.
Right. So my question is that we know that the minimum spanning tree, we know that given a graph, it could exist in multiple minimum spanning tree on the graph. But maybe it has been, maybe we let it go. Maybe I think maybe we let it go. We do not need to stick on this. Okay, keep going on.
Okay. Let's talk about the Codebert architecture. It just follows the BERT and the Robota, just the same model architecture. It is multi-layer bidirectional transformer. And if you're interested in transformer, we can have another discussion on this topic. For Robota, I just said some advantage of the Robota. It is an optimized version of BERT with more data, larger batch size, longer training sequence, dynamic masking, and no NSP. So this is another task we just discussed. Besides the masked language modeling, this is the next sentence prediction. The Robota says that no need for NSP because it is trivial. Okay, so and the byte level character. This is a very interesting optimize because that means that will no more unknown character. Could you unknown? That means every word will know. Okay.
Okay.
So it is the byte level, not a Unicode character. Okay. So next we will talk about the input and output of the model. Here we just copy the architecture from the BERT. The input should be like word 1, natural language word 1, word 2, word 3, like this.
Still the one hot vector. Still the one hot vectors.
Yeah. You should know that there is a dictionary. Okay, that dictionary now is maybe it's a BERT is a byte. Okay, this is for byte level, but for better understanding, you can just think it's a word W1, W2, and here is the one hot vector.
So what do you mean by the byte level?
If it's a byte level, then it should be like 0001. This is 1 byte, and then it get a vector, one hot vector, and 0010. It get a how to say one hot vector.
So what's the difference between the traditional one hot vector?
Now there's no word. There's only byte.
So
no word, no mine. The mine should be 2 bytes if it's in English.
Yes.
So there's no.
But this. Oh, the point is.
Convert the byte.
So it's more like character level, right? So it's more like
Character
so
level.
the byte is more like character level. So, but there's the. Oh, okay, I see. So the space will be another kind of the byte.
Yeah.
Right. Okay, I see. Got it.
Okay.
Mm.
Then the second sentence should be code 1, code 2, code 3, and then go on.
So
And
each character will be got a vector. Will be got an embedded vector.
what? Pardon, please.
So more like if we go to the byte level, it means that we can the whole vocabulary will be only 256 if we English have only that's the whole vocabulary size, right? 256. So it will shorten our vocabulary size, and there will be there definitely will be no unknown character.
Yeah.
Okay, so the rebuttal is trained on the character level or the byte level, not on the token level or word level.
Yeah.
Oh, I got it.
Okay, so the output is the contextual vector representation of each token and the representation of CLS. So the output should be the new word embedding, as the new byte embedding of W1 dot W2 dot like this.
So more like C1, C2, like.
Yes, C1 just means C1 dot C2 dot. It's all byte level representation. Okay.
Yeah, but when you try, so I'm thinking about the loss function. So it is a character level. So it means that we have to use some transformer or some RSTM to do to compute the loss, right?
For my understanding, I always think it's just compute the similarity loss, like cosine.
So
Like this.
when we pre-train, so that means that when we do the pre-training task, especially for the downstream task, we need to compare two sequence of characters instead of two words if we are doing the token masking prediction task. Right? If we go to the byte levels, and the output is supposed to be a sequence of a character.
Yeah.
So okay, keep going on. I will do not linger on this if it's not too much. There's not too strong relation to the Codebert.
Yeah. So this is the input and output. For the pretrained data, it used the data from this paper, and here is the statistic of this data set. You can see that the bimodal data is both natural language and code pairs, and the unmodal data is just only codes.
You mean unimodal?
Of unimodal.
Yeah. Bimodal and unimodal. So here, can you specify pairs? So can you elaborate more about the bimodal and the unimodal?
For the bimodal, it's just like this example we have just talked about. It's a two sentence. One is the word, one is the natural language, another is the code. Okay, this is the bimodal.
Oh, you're not talking about the Codebert now.
No, we are talking about the Codebert.
Yeah, we're talking about the Codebert.
Yeah, the Codebert model architecture is the same as BERT. So we just use the picture of BERT because the Codebert didn't provide a picture. You can
okay. The input is the programming code now.
Yeah.
Okay.
You input both the natural language and the code.
Okay.
Okay. So for the unimodal data, it uses the replace token detection task. You can regard it as a downstream task.
Okay, so this token is for program token or natural language token?
Pardon, please?
So this token replacing, we replace the token in program source code or in the natural language?
because it's a unimodal. If there is only natural language, it just replace the natural language. If there's only code, then you replace the code. Okay.
Let me digest a little bit. So
I can.
So why do we call it a generator? Because we're going to generate or predict the masking token.
It just follows the it is adapted from the GAN. So it is a generator and a discriminator. It is adapted from the GAN, this task model.
And what does so the GAN will be there's a GAN between generator and discriminator, and what's the role played by this discriminator, and how the generator will utilize the output of discriminator.
The generator could be like a sequence model like LSTM or transformer. And in this paper, it's just use the n-gram language model. And for discriminator, it is just
by the way, so here, so maybe you can go through from the very start. So there's a lot of confusion here. The first is that what's the difference between, so I still somehow a bit confused about the bimodal and the unimodal. So only one option. So
it's the model DAL. That means it has
a model. It's a model. It's not a model.
Model. Yeah.
A model data. All right.
So, I just keep going. For this example, it shows bimodal data NLPL pair. You can see these examples. Here is the natural language. Here is the code. So you just input the natural language and input the code to the Codebert as a pretrained sample. And here is the two pretrained method we have just talked about using the different data. So let's talk about the replace token detection. There are two data generators here. One is natural language generator, and another is the code generator. Both generator, I have just said, they can use like sequence model like LSTM or transformer. Also can use as language model like N-gram. And the discriminator is trained to determine whether a word is the original one or replaced. Because you know the actual sense, you know the truth, and you just, this is the prediction. This is the truth. You just copy just calculate calculate the loss. The formula is below. The first is we talk about the formula of the mask language model. Given a data point of natural language program language pair, here we use the X equals to WC. W is the word, that means natural language. C means code as an input. And then we first select a random set of position for both natural language and the program language to mask out. Here we just randomly select. And then we, it follows the BERT. About 15% of the tokens are masked out. And then the MLM, the mask language model objective is to predict the original tokens which are masked out. This is the formula where the PD is the discriminator which predicts a token from a larger vocabulary.
So here I'm a little bit, I feel that somehow lost here. So we can go to the previous token, previous slide. the previous slide. So here, so I'm still keep asking for your illustrations. So these NL generators and the code generators are going to recover the masked sentence, right?
Yeah.
So giving this is comment, this is code comment, and this is the programming code, the
Yeah.
code, right? So we randomly mask some tokens, some word in comments and some tokens in program, and the NL generator and the code generator are going to recover the masked word and the masked token. Hello?
Yes, I think so.
Or this, what do you mean by sample? I'm quite, so or this is generator or just randomly picked some model. So here, so let me asking. So this W1 has been masked, right?
Yeah.
And does NL generator a neural network model or a random sampler?
Not random sample, it just predicts the word.
Okay, it's predict the word. Okay.
Yeah.
So suppose it predict W1, the position of the W1 to be WS1, and why this would be W5. So I
W51 because it predicts wrong. It should be W1. It predicts the
okay. So anyway, so it predicts wrong.
W1, yeah. It predicts wrong. It's replaced. That means the discriminator thinks this word is replaced. It's not the original one. But if you predict W5, that means it's original because it's the original word. It's the same like this is 162. This is replaced.
So for the discriminator, it will predict for every word, for every token, every word in the comments, or every token in the program source code will say whether this token is natural based on its context.
Yeah.
If it's not natural, it will think it's replaced, right?
Yeah.
And also, and in this case, and how does the okay, so the bird, and even if we got the replace or not, and how do we use this information further?
So this is just Xiangling just gave us a picture cat. For this task, actually, it is a discriminator. It's just not a generator. It's not just a generator.
Yeah, I understand. The discriminator can see whether it conforms to the distribution, right?
Yeah, it's just a discriminate whether the word is replaced or not because you have the choose. So during this training, the generator will be better and the discriminator will also be better. So it just utilize the discriminator to optimize the generator to generate a better word embedding. Could you understand this process?
But here, so the token, the W and the C we will have a random. So this C1 or this CI and WI are embedded vectors, or the are all embedded vectors, right?
Initially, it is just follow the dictionary, byte level dictionary. So during the training, the embedding will be different.
Oh, by the way, so if it's by levels, is that possible that we remove certain characters?
Oh, pardon, please.
The characters, for example, I'm saying that hello world, right?
Yeah.
So in this case, this hello world will be considered, this is 5 characters, and this 5 characters.
Yeah.
So in this case, the hello world will be 2 tokens or 11 tokens, because this space is another token. So giving these comments,
the space is also a token.
Yeah, I understand. Space is also a token. So this is so hello world will be considered 11 word or 2 word.
11 word.
11 word. Okay. Yeah. So if we do the masking, so that means we will sometimes mask O, right, or mask L.
Let me check. I'm a bit confused. Though it said it follows the architecture of Robota, but in the example, actually, I think it's just a mask word.
Yeah, I also agree with that.
Yes, those he just said he follows the architecture of Robota, but he gave an example, and the example shows that it follows the just this example. Just mask the MIN. That means it's a word.
It's token. So the token. So let's synchronize the terminologies. So the unit in the program we call it token, and the unit in the natural language we call it word, right? So okay, let's go back.
Okay, so maybe this is a problem. The paper does not say much about the framework. Yeah, it just said it follows the Robota, but it didn't give anything about the model architecture actually.
Okay, so let's go back to no, we still have a question for the approach, because I think this slide is the most important slide for the approach illustration, right? Giving your presentation. I think the slide 23 will be supposed to be experiment now. So here, suppose that the word and the WI and the CI is supposed to be the word and token here. So in that case, how do we embed the the embedded vectors for word is supposed to be straightforward, but how about embedded word for the token in source code?
Actually, why do you say it is a byte level representation? Because I didn't find it in the paper.
What level?
Byte level.
Because it said it follows the robot architecture, but if you read the robot paper, it said it follows the byte level. So I just said I just think the paper will be byte level.
Oh, did you look at the code for Codebert? So do they actually use the byte?
No, actually no.
Okay.
I think we need to
Never
grasp
mind.
this idea more, but I haven't think about it. So anyway, when we read papers, we do not just read it for per se. We need to read papers for the sake of our own research. So let's keep going on. So I'm still trying to digest the generator and discriminator stuff.
Okay. So any other question?
So when we optimize the discriminators,
how we optimize? Do you mean this?
Yeah, let me think about it. So suppose it's very beginning. So when we train the discriminators, the discriminator is supposed to start with let me think about it.
You can.
So the output of all the feedback of the discriminator is supposed to be the input of the generator, right?
Yeah. What do you mean? You mean the output of the discriminator?
So my point is why we need a discriminator here? Why we need it? Why we need it? For example, if we're using BERT, suppose let's consider as if we're not talking about the Codebert, we only talk about the traditional BERT. So traditional BERT do not have the discriminator.
Yeah.
Right? So as long as we do the masking, we predict the mask and we calculate the loss of the predicted tokens and the real mask tokens, and we will get a loss. We will have the loss, and we can do the optimization, and that's all. And what's the role played here? And also for code generators, if it's code generators, I think we also do not need discriminators. We mask some tokens and we predict again, and that is also fine. So what's the role of this discriminator played here?
Yeah, because the paper want to use both bimodal and unimodal data. If
So,
you use the bimodal data, we can just use the up this part. We can just use this part. But if we want to use the unimodal data, we should just combine this to like.
okay, so if we can use, yes, suppose we use a bimodal model. So let's say it's bimodal. If we look into the bimodal or the data and the and how we associate the natural language and how we associate the code, the source code and the natural language, or the source code and comment, and how can we make the connection link between these two kind of materials?
Okay, first, actually, we don't have just only natural language because most code with no comment.
Yes.
Yeah, so we just use the code generator.
Okay, so for code generators, we can only predict the mask the token, right?
Yeah, but if we just use the it's just the same as the it's the same as the bert. So the discriminator is just like optimize the masked language model.
No, the problem is that so giving you output, the input is the NL code discriminator. So if I understand correctly, this NL code discriminator take input of both the comment and the code, right? And all the and somehow it will predict which token and which word has been replaced, right? And I didn't see how the embedding vectors are generated by this way.
Generated by this.
Yeah, for now, so this word is somehow like a one-hot vectors because we have a category, and this token is supposed to also have a one-hot vector. We're supposed to also build a vocabulary for the source code, right?
Yeah.
And by this means, the aim, the goal is that we for each token in the programs, I don't know the unit for the code unit for embedding, but whatever it is, we need to learn an embedded form of the code or into the world, right? And
Yeah.
how this architecture can provide us this information. And also, I'm still very curious about what role does this discriminator play?
Okay, first for the bimodal data, then this is a whole architecture will be used. You just input the word and input the code. So during the training process, you just you first mask some word, and the generator should based on the context to predict the new embedding.
So you are still using the word predict, but why the label say the sample? This label called sample. See, this is called sample.
I check is trained by detecting the token sampled from.
So just like the traditional GAN.
Maybe I think maybe the generator just find a word in the dictionary. So
my guess, but I didn't read the paper. My guess is that given tokens and mask and it replaced the mask positions with random word. And we're going to see whether the discriminator can predict that this word has been randomly replaced or not. But I didn't got how this generated discriminator work and how this GAN-based idea we used to synthesize to learn the embedding.
You mean how the model learns the embedding of the word?
Yeah, how because the Codebert is just to learn the embedded version or embedded representation for the comments and the code, right?
Yeah.
And I didn't see given that because giving these architectures is all there and there definitely is some information loss.
I think if you look at the formula, it first, let me see first. It first generate. So it first generate a plausible answer alternative for the set of random mask position, like here. And I think I also a bit confused.
Yeah, I think you haven't. I'm afraid that you haven't fully digest the idea of the Codebert, but somehow you can see the corrupted. So there's a corrupted idea. The corrupted words, X corrupted. So that means if we are training the positions, let me see the formula. Let me look at the formula for 5 minutes. I think let me got a point here. So can you explain yes corrupted the word?
This is the generator. G is the generator. It generates the masked it based on the masked word and generate the new word here. And then it corrupts.
I somehow got the point.
In the place,
I somehow got the point here. So that means we are by this approach we are force the generator to make a better prediction.
Yeah.
Make a better prediction, but I still not understanding that why we need to concatenate the corruption, the comments and the code. Why we need to using such a simple operation by just concatenate the comments and the code. I still didn't get that point.
Because we want to get the relation between the code and the natural language. Do you
definitely we want to do this, but why concatenation is the choice?
What is concatenation?
Concatenation means that we suppose we consider this string 1 and this string 2. We just got a string by string 1 connected followed by string 2. And that's a concatenate.
Yeah.
Concatenation.
Just like the bert just concatenate two sentences to one sentence to predict. That is.
Then this paper is published in EMNLP. Concatenations just work.
What does mean concatenate?
Concatenation means connection. We connect the comments with the code.
Because it's a sequence model, we just concatenate two sequence to get the relation between them.
And also, is there any relation between the mask, the W and the mask, the C? Is there any relation for that?
No, it's a random choice.
Yes, it's a random choice. So how do we build a correspondence between the comments and code? Suppose I'm saying that there's a word saying that we are calculating the max of the max, calculating the max array of the max element in the array, and there's supposed to be a very long implementation for the specifications. And how do we build the connection between the source code and the source code and the comments? There's no obvious link between the code and the comments.
Because it's a sequence model. The first, if it is a transformer or LCM, that's like the same word. The first word, the information will transmit to the second word and then to the third word. It just transmit to the following words.
Yeah, then how do we know?
So if you predict this word, you just have the information before. If it is just one direction, if it's bidirection, you will have the both side information.
but it is a generator. If it's a generator, we just using the, let me see. So which part in the formula is the generator? So maybe you go here, go this 21.
This is for mask language model.
Yeah, you can see that it's like a cross entropy. You have likelihood and you have cross entropy.
You mean this? You mean this is a?
I mean a loss function, yeah.
Yeah. Let me check.
Here is discriminator. No, this discriminator is going to see whether.
No, I think this one is generator, right? So when generator is trying to compute its loss, it depends on discriminator. So we fix the discriminator and compute the loss for generator. That's how we do it in GAN, right?
Yeah. This is for mask language modeling. It's not for the replaced token detection.
Yeah, but at the end of the day, you need to sum up the two losses. So your total loss is equal to loss of MLM plus the loss you shown in the next slide.
Yeah. But it's a two process.
Yeah, so it's like you have two conflicting goals to optimize in your GAN network.
Conflicting. Why it is?
Definitely it's conflicting. Definitely conflicting because the discriminator trying to distinguish which one is the masked one, and for the generator is going to optimize to try its best to synthesize a token in a masked position, which can fool the discriminator. So they're conflicting objects.
Yeah.
So here, I think I almost got the idea of these tasks. I think I almost got the idea of these tasks. But my concern is that, does this word are embedded tokens or embedded word?
What's your
I mean
problem?
the token here. The token here is supposed to be embedded. The word is embedded in, suppose the WI and then CI are supposed to be the embedded vectors, right?
Yeah. Yes.
Okay. So my last question. So I assume that I think somehow I got it. I got the idea. So the question is that for the word or natural languages, the vocabulary is kind of fixed, right? We have a dictionary, we have a vocabulary. But for program tokens, and how do we construct the vocabulary?
Like if you just said int a equal, you just this int will be in dictionary. This a will be in dictionary. This equal symbol will in dictionary.
So there will be a so the problem is that the program, the vector for giving a normal book or giving comments, its vocabulary is limited. The size of vocabulary is limited. But for program source code, the giving the naming conventions, giving the method names, its vocabulary is almost infinite. The size could be low as well. So the problem is that how do they define its own vocabulary?
So originally I thought it's the byte level. So if it's the byte level, then there's no unknown token. Secondly, if there's too many words, if you want to word level, then you can have like split, just do some efforts to change the name to to change the like variable name to the word in the dictionary.
But for the second approach, I think it cannot address the problems fundamentally, because it largely depends on the naming convention used by the programmers. But for the byte levels, it seems that it introduce a lot of complexity because we're not predicting each token. Especially for program, I think the token is more important than the character. For example, the int. The int itself is the keyword, and the int actually means almost nothing in program. So in this case, So somehow I think I suggest, so I got a big picture in your suggestions, and also personally I can give my comments on this word. I think this word does not address the problems fundamentally. My first concern is that the concatenation. So giving its formulas, it just concatenate the comments with the programs. There's no direct correspondence, or there's no fine-grained correspondence between the source code and source code and the comments. For example, suppose a large piece of giving a large piece of the comments and a larger piece of the code, and the correspondence between the specification, the comments to its code implementations are lost. So by this means, I think the model can hardly capture the direct relations between the source code and the comments. If we're going to do this, we somehow need a way to have a fine-grained correspondence between the source code and the sentence, the source code and the sentence. So that will be more details. And second is that it seems that it can be, I think the task itself could be fine, but we're supposed to be, I think there's supposed to be a better way, and this is very rough work. But even for this work is quite rough, it is still published in EMNLP. So I think the work is now quite publishable as long as we have the idea.
Yeah. For the concatenation, I think it just follows the architecture of BERT, because when BERT concatenate two sentences, it just concatenate. So yes,
because we have different principles. If we would like to, so what's the goal of the Codebert? So the Codebert, so somehow, for example, if we're giving the natural languages, definitely we can use context information to infer the distance between a king and a queen and a boy and a girl, and how this idea can be applied on the code. I didn't see that. Maybe we can find the idea of for and a while. They have full semantics, but definitely the code itself should go beyond for that. And also the single token for the program, then a single word means something, but a single token like A and B, for example, a variable A and B, doesn't mean anything in source code.
Yeah.
Right. So for this work, I think it's hardly captured anything meaningful. Despite
no, I think the token here is a set of characters, not a single character. A token is like you split by some special character, then it forms a token. So you can understand token as some kind of word.
Can you raise an example for token? For int.
Like in your
suppose like
programming language code.
Yeah.
Maybe you will split the
A and B. So do you think so? This will be 3 tokens or 1 token?
A equal to B.
Yeah.
Oh.
I think it's 3 tokens in most.
Yeah. So in that case, C equals to D, right? So this doesn't mean anything.
But the equal means something, right?
Definitely equal can mean something.
Yeah.
But also,
if you have equal, then definitely you will have a variable on the left and a variable on the right.
Okay, so suppose in this case E equal B sometimes has equivalent meanings like value equals input, right? Or something to means that maybe the name equals X, or balance equals or whatever. So do you think they have the same semantics?
I think it also depends on the class of the variable.
Yeah, I think it's largely depends on. Yeah, I just feel that there's a lot of work just to borrow the NLP architecture or framework, and actually it is not that.
But I think the way they design the laws is very smart. That they are trying to combine two goals together.
I understand. So let's go back there, Yufan. Go back to the slide 20.
Okay. So this is one of the tasks. Another task here is a mask language model. So So the generation, this generation is not computed in the final loss.
No, so the
Why?
generation is supposed to be one of the loss, right?
Yeah, it's the MLM loss.
Ah, wow.
Yeah.
The MLM loss is not this.
You go to slide 21.
This MLM loss is not the it's not the NL generator, I think.
What is the full name for MLM?
MLM is the mask language model. It's another task for, it's the objective one, if you check the paper. So that means this is a two task. It just combines the two task loss to one.
Yeah, that's what I said.
But yeah, so but the NL generator is not the MLM.
So here the first model is going to pick up the mask. Sorry, let me ask. So the token. Is there a model for us to select how to mask the token word? Randomly choosing the mask word, mask the position.
Just a randomly mask.
Randomly masked. So then what does MLM do?
I mean, that's a two task. The first downstream task is LMM. The second downstream task is RTD. The MLM task we have just talked about, just talk about like this.
Exactly like BERT.
Yeah, it is the same as BERT.
Mm-hmm.
Yeah, it's same as Robota. So this is the first task, and the second task is this. So this part, I draw as the blue line. This part is not the MLM. It's just another task. It's a generator and a discriminator architecture follows the GAN. So it's different, totally different. Could you understand?
So here, if we are using bimodal corpus.
Yeah.
So it means that we need to build the links between the comment and the code.
Yeah.
Right. And then by right, so suppose I comment some comments, I should comment, or sorry, suppose I mask one word in the comment.
Yeah.
I should mask the corresponding program or the set of corresponding tokens in program so that we can build the links between the source code and the comments.
But it just try to learning the contextual information of the code and the natural language. Just learn the contextual information, not prediction.
But why ML? But if it is just a context information, why we just use MLM? So that's all for context information. And why we need to build such a ROD, so whatever the name it is.
Token detection.
Yeah, why we need to use a GAN-based approach?
Because
and why by the bimodal is that supposed to be provide additional information, more information than the MLM, right?
Yeah.
And if we just randomly mask those tokens, what does matter to do this?
Because the meaning of mask is to predict the mask word. That means you mask the word. You want to try to get the new embedding of this word.
Let me think about it. So
it does not mean that you should correspond to the code, but I think it is just a.
I think a more broader way. So could you go back to the slide 20? So a more, if I'm the one who designed the approach, how I do this. So I will fix all the code here, and then I will mask so when we mask the word, I will not mask the token, and when we mask the token, I will not mask the word, so that the word information can be used to predict that masked token, and so the token will be used to predict the mask, and that will be my design.
Yeah. I think it is also follow this this method.
Yeah. I think it's not meaningful to mask code, right?
But if you use to generate code, you can mask the code. Could you?
Oh.
Yeah.
And also giving the token, suppose, so may I ask, so if we're using the compiler principles in what the integrated course, so how do we mask the bracket? Will this bracket be considered as be masked and to be predicted?
Yeah, it will also mask this symbol, and want to predict this symbol.
And also,
I think
and what's the point to provide an embedded version of this bracket?
Because maybe like it's just if you write in C++, this symbol means that the variable will be effective just in these two symbols. It's just this is meaningful. I think so. I think. And what you just talk about is just one of the experiment actually. Maybe I can first finish the experiment.
Okay, maybe let's stop talking about the approach. Let's go through the experiment.
Yeah, the first experiment is NL code search. The definition is given a natural language as the input, find the most semantically related code from a collection of code. So I think this task is just follow what you just said. It's masked one code. If you know all the natural language and mask one code. The data set is the code search net, and the metric is mean reciprocal rank. This metric is very usual in the search task. Here I give an example. Sorry.
So if he is going to search,
Here is an example. Here example, this is search. This is a query. Query is create a file and write something. Then it will search these two codes. This is the example for a code search.
Yeah, for code search.
Yeah.
So here I have a question. So how this piece of code can be encoded? Based on the Codebert, how this piece of code can be encoded. Intuitively speaking, so based on the BERT, we'll modify it into a sequence of token, right? A sequence of embedded vector, right?
Yeah.
Supposed to be v1, v2, etc., vn, right?
Yeah.
And this one's supposed to be another piece of code, right? A sequence of vector, right? Suppose I'm saying that it's called O1, O2, and OM, right? And how to use this query to compare the similarity, calculate the similarity with this vector.
Yeah, I think there are two ways. One way is to first input the sentence, input the like v1 to vn to input this sentence v vector, and you will get an output. Okay, you will get output of the Codebert. You may get a sequence. Then you can just find the most related sequence of the code. Because
I didn't get it. Will you please say it again? So giving a v1 as a vector, then
you input to the Codebert model, and you will get output of a vector sequence. Yeah.
Yes.
Yeah. So this output vector will compare with the data set and find the most related vector sequence.
How?
Because all the code in your data set has been transferred to vector sequence.
Yes. So how do we compare two vector sequences?
You just like cosine. I don't know.
There's no dimension. Their dimension is not the same. Cosine is not possible.
Oh, you mean the dimension may be different?
Yeah, the dimension it definitely be different because the length is different.
Yeah, so maybe it's just use the Vn because the Vn concatenates the whole sentence meaning in sequence model.
No, I don't think so. So Vn is just the embedded vectors generated based on or constructed based on the previous one. For example, I'm going qualifier and right is going to predict something, and it is just the form to that it is just the embedded form for something, and the qualifier and right are definitely different vectors.
In the paper, it just said it used the CLS, similar as what I said. CLS is the model in the beginning of the sentence. This is, could you? Yeah, it thinks that the CLS token just conclude all the sentence.
How could it be include all the sentence?
Because it is a sequence model. In the sequence model, the meaning, the information of every word will transfer to every word if it is a bidirection. So it's just a concact.
So we have one more presentations, but I think there's I will leave a few comments here for you to for us to investigate. So I suppose that we can clarify this point during our individual meetings in next week. I mean the next Wednesday. So let's pause question. I think we now need to put aside the questions and keep going. Let's finish the presentation.
Okay. For the next experiment is natural language programming language probing. And here is the definition, and you can regard this as the multi-choice question answering task. This is the example. You can this vivid example shows that the choice will be max, mean, less, greater, and the model collect one of them. The input is the complete code and a masked natural language document. In this example, that means you just give the whole code and mask this word and let the model predict this word. And here is the experiment result. It shows that in this example, the Codebert based on LMM task, it means that it pre-trained just on MLM task. The MIN is the most probable choice. It shows that it outperforms the Robota. In the programming language task, it's the same. You just predict the mean. Also, the Codebert outperforms the Robota. For the experiment, two results is just here. And here we can see that the probing, the PL probing with preceding contextual only this line. Here, the results show that the Codebert is not the best. This paper just said it is a challenge task and no further analysis on this. And the experiment 3 is though the Codebert is not designed for generation, the other also do something about how to generate documents. It used the smooth blue score, and the result shows it is the best. I will give you some example. The first example is here. if you input this code, and the Codebert will definitely the same as the golden label. For the second example, it's the same. You can see in the statistic data, if you use the loss of both RTD and LMM task, it will have the best performance. For experiment 4, it just generalized.
Hey, by the way, Yihao there.
Yes.
So if I want to please go back to the previous slide. So according to the traditional approach, how do we embed tokens or program tokens when we are using the existing model?
Usually the tokenizer we use will cut the word into subword and convert them into embedding. So the basic unit is the subword. Right. If we have a very long for function name, then the function name will be cut into, it will be split into several subwords.
I got it. So we first do some tokenizations, and after tokenizations, we further split the word based on the camel conventions or the underscore convention. And after we do that, and how do we embed those tokens?
How do we embed those tokens?
Yeah. So we got a program source code, right? We need to feed into the, and need to numerize it or vectorize those tokens.
Some similar techniques like word to vec.
It's not one hot, right?
No.
So does it use bert? And what technique is to transfer word to vector?
One choice is have a dictionary. It is a trained vector. That means this is the word, this vector. They are all fixed. They are trained on a large corpus, and you get just use the final result.
Yeah, but how does the baseline do? How do you know that?
Not
it's okay.
Very sure.
It's okay to say no. Do not need to invent some new idea. So yeah.
What's the meaning of baseline?
The baseline is Yihao's baseline. So Yihao has some baseline to work on that. So this embedding is more like a tool just to transform a tokens into a vector to facilitate the training. So that's all.
If you use a bert, you just input a sentence. You just input a sentence and get a new embedding of the sentence. In here you use the CLS.
So all the sentence will be turned into a CLS.
Yeah. After split the token, like.
Okay.
Then it uses the CLS to predict the final result. And for the experiment 4, it evaluates Codebert on the programming language which is never seen in the pre-training step. The result shows that the Codebert is better than Robota, but worse than Code2 sequence. It said that the other analysis that the Code2 sequence make use of composition paths in the AST tree, while Codebert only use the original code as the input. So he said, the other said this shows a potential direction to improve Codebert by incorporating AST. I think we just talk about this. We should not just concatenate the two parts. Maybe we should make use of the AST tree. That's all for my presentation. Thank you.
Okay, thanks, Yufan. So I suggest that because this is the first your paper presentation, so the first thing is that because we all recorded the videos, if you make an excellent presentation, of course your presentation will be good, but definitely we can see that you got the general ideas, but not so detailed. I think so. Wang Chao is not here, but despite Wang Chao will have some his own trick, Wang Chao has his own trick. But the overall idea, I think one advantage or one good point of Wang Chao is that I know he didn't finish reading all the paper, but he can always give the big picture very clearly and avoid my questions as much as possible, as many as possible. But for your presentations, now this is the first time you do the presentations and also maybe in English, maybe. But whatever it is, I suggest that when you read the paper, clearly you somehow lose some important details of the big picture. So that's why we linger on these presentations. In most of the time, we're guessing, we're inferencing. So there's a lot of unaddressed problems. So I leave a few questions so that we can discuss more in our next week individual meetings. The first is that how the code bird can be used. So for example, given a piece of code, they whether the code bird will be summarized this code into a sequence of vectors or one vectors, right? Because given your task, it has predictions, it is used for code search, right? And if it's for code search, how can we compare two sequences of vectors of different lengths, right? This is the first question.
Okay.
Yeah, so we need to clarify this in our next individual meetings. And the second is that that's my comments for the Codebert. I think the idea of game-based approach is novel. I agree it's novel, but I still feel that it's missed the link. It somehow missed the link between the comments and the code. Usually, if we are doing the code embeddings, it means that the code of the same semantics should be represented by the same embedded vector, right? And how this approach and very straightforward for code for the bird to do this, but how Codebert can do this is still kind of that a little bit a little bit unclear, right? Especially for two pieces of code. And one code is good. For example, we are implementing quick sort, right? If we are implementing quick sort, we have two versions. The first version is about recursive version, and second version is stack-based version. And how can we mix them together? And usually, the best way is that based on comments, we know that both are quick sort. But in this case, and how do we? And this model, I think that it's very hard to say that this model can capture such a commonality, right? So maybe in the future, and for Yufan, for Yufan. So one of the important topics for you to work on is that given two pieces of code, and we do not need to synthesize new code. How do we automatically combine them or seal them together so that they can construct into new function? And that will be a very interesting. And maybe we also need to think together about how Codebert or how what2 vector what role can the what2 vector play in our this task. Maybe it is yeah, maybe I think it's just more like a search for. Okay, so let's talk more in our individual meetings. So let's invite Yihao to give us the next presentation.
Okay, thank you.
Okay. Should I start now?
Sure.
Okay. So hello everyone, my name is Yihao, and today I will present the paper SIT3 code summarization with structure-induced transformer. It's a very new paper, and I didn't find it is published on any conference. So the author of this paper is from Shanghai Jiao Tong University, and two are from Shanghai Jiao Tong University, and one is from Suzhou University. And Wu Hongqiu is a PhD candidate, and Zhao Hai is his supervisor.
Mm.
So let's first look at the background of code command generation. So in early days, people tend to use template-based method and information retrieval method, such as code clone detection techniques to find similar code and use the command of similar code to do code generation. And in more recently, the neural network method is proposed, especially the encoder-decoder framework. The sequence-to-sequence framework is proposed to tackle this task. And generally, we have different types of neural network models. So RNN-based model is one of the types. It is sequential, means that the input of the model is sequentially being inputted to the model. And one of the drawback of this model is this types of model is that it will lose information on the long sequences. So it cannot have long dependencies on very long sentences or long code. And the other type is transformer. Transformer is another type of encoder-decoder framework, and it is non-sequential because it is bidirectional. And but one drawback is that when we want to combine the AST to transformer, it will not work well because when we want to input the AST into transformer, we need to use the technique called structure-based traversal. So this technique will transform the AST, transform the tree into a linear sequence so that it can be fed into transformer. But transformer itself is non-sequential. So there is some mismatch between the input and the basic feature of the model. So it doesn't work well. And another type is the tree LSTM. So this type, it can itself can directly model the structure input of code because so that we can directly input the AST into this tree LSTM or graph neural network. But the drawback is that the tree LSTM has the same drawback as the RNN-based models. They will lose information in long sequences. And the drawback of GNN is that they are only sensitive to local information. So so the paper has summarized the different characteristics of different types of model here. So we can see that the transformer has the long-term dependency, but it does not have structure-sensitive feature because it does not incorporate the AST into the input of the transformer. But when we want to incorporate the AST into the transformer, that becomes the SBT plus transformer, the second last row of the table. Then we can see it is structure sensitive. It is long-term dependency. It has long-term dependency, but it does not match the feature with the model. So the FMM here means feature model match. As I just mentioned, the SBT is a linear sequence of AST, and transformer is a non-sequential model, so it does not match. So the paper here wants to present a model such it wants to modify the transformer so that it can solve the feature model mismatch problem here. so that the transformer can take in the input of AST.
Okay, please go on.
Yeah. So before we get into the paper, we recap what is the transformer encoder. So here, let me draw something. Here, here is one layer, one stack of transformer encoder, and on the right graph is the mechanism of attention calculation. So in transformer encoder, it has 4 subsections. One is the multi-head self-attention, and it has the feed-forward layers and the layer norm and residual, and the positional embedding. We can see the respective modules in the graph. And how do we understand self-attention is that if we input if we take the natural language sentence as the example, here the sentence is, the animal didn't cross the street because it was too tired. If the model wants to understand the meaning of it, then the function of self-attention is to calculate how many attention we should pay to each of the word of each of the other words in the sentence if we want to understand the word eat. So here, based on the attention score, the model thinks that we need to pay more attention to the animal here and pay less attention to the because words and some other words here. So that's the self-attention, the intuition of self-attention.
We please go back to the previous one. So which layer is the self-attention? Which layer is for self-attention? Giving the transformer. The multi-head attention.
Yeah.
So somehow I forgot it because it's a long time before I get myself familiar with the transformer. So how does the self and what information does the self-attention layer extracted to make to facilitate or improve the prediction?
So the self-attention will generate the attention score for each of the word. It will generate attention score.
It will generate attention because it's not for attention. It's not attention layer. It's a self-attention layer. So self-attention layer capture the information or capture the relations between each two any pair of word in the sentence. Right?
Yes.
So how does the information can provide us more? How does this kind of information can improve the prediction?
Can improve because so in this way the every word has the contextual information of the other words in the sentence. Because
we can only now focus on
interact with other words.
Focus on just an example. The token it has a relation with the animal, right? And how this information can be further facilitated for prediction. If you have no answer, you just keep the questions. We keep going on.
Okay.
And we can answer the questions. Maybe you can just feedback the questions later.
Okay.
In the group that is all fine, or maybe you can discuss with more details during our individual meeting.
Okay. So here is detailed calculation for attention. So here we can see that we have we have a value, we have a key vector, we have a query vector, and based on this formula, we calculate the attention vector of each word. And the multi-head means that we use different set of weight W here for each head, and we do the same attention calculation for each head, and then we concatenate each head, all the head together to be the final output of multi-head attention.
Mm.
So after we know the background of transformer and the attention mechanism, the paper, the approach of the paper is quite simple. So it has proposed the structure-induced self-attention module instead of just a vanilla self-attention module. So the only modification is in a formula here. You can see that in the original formula of attention, it takes it uses the Q times K divided by the a dimension and take the softmax, and V times the V outside the softmax. So the only modification of the formula here is it add the matrix A, and this matrix A serves as a mask to the attention module. So what does it mean? Originally, the attention module, we can view the self-attention as a complete graph as depicted on the left side, because every word is calculated against every other words in the sentence. So here the complete graph means every node here is connected to every other node. But because there are some node is less important, and we want to integrate the structure information into this graph, which is the AST tree. So when we want to integrate the AST tree into this graph, then we can, based on the information of AST tree, to cut some of the edges, which is not in the AST tree.
So somehow we manually using the AST information to reset or clear certain ways in the attention matrix.
Yes. Then we, based on the AST tree, we generate this mask mask matrix A, and we use the A times the we incorporate this this mask in the self-attention module to drop out some of the attention weights. Yeah.
Okay, keep going.
So the overall structure of this this paper is like this. First of all, we have the source code as the input, and then we have 6 layers of transformer encoder and 6 layers of transformer encoder, and then generate the summary. This is the overall structure, and the modification is in the transformer encoder. So here we have 3 stacks of transformer we have 3 stacks, and in each stack we have 1 layer of normal transformer encoder and 1 layer of structure-induced transformer encoder, which we which I just mentioned on the last slide. And here, so the first stack will use the graph of AST tree, and the second and third stack will use the control flow graph and the program dependency graph to generate the matrix, the mask matrix A. So here some information is losing here because the paper put the generation of this multi-graph JSON matrix into the appendix, but the appendix is not in the paper, and I also didn't find anywhere. So I'm not sure how they, based on the control flow graph and the program dependency graph, to generate the matrix, but the idea is here. And then they combine these two layers as a stack and repeat this stack for 3 times. Each stack uses different graph. And the way they combine the 2 layers is use the concatenation. Yeah, that's the overall idea of the paper. And
so here, what is the word-to-vector? Do they use word-to-vectors? So how do they embedding the source code?
the embedding is also the same as the transformer in the
use bert to do the draw.
No, there's a work in transformer in 2020 also takes into the code and generate the output, and they use the tokenizer in this transformer.
Okay.
Yeah, and so the result is shown in the table. So here the transformer is only using the structure-induced module, and the SIT3 means we combine the 2 layers into stacks and use three of the stacks. So you can see that when we combine when we combine 2 layers together, improves the score. And the paper also did some ablation study on the method. So here V means vanilla transformer and S means the structure-induced transformer. So here, if the all the 6 layers of transformer encoder use the vanilla, then this is the blue score. And they have experimented with different configurations and found out the 3 and 2, the 3 structure and 4 structure induced transformer is the best.
Okay, so this is more like the minor. Of course, from the high level, it's minor, but for detailed empirical configuration, so that'll be important. Keep going on.
That's all. And the right table here is they have experimented to use different masks. So they replace this structure-induced mask with some other masks like Gaussian matrix or random matrix. So they have validated that the structure-induced mask is the best. Yeah, based on the scores.
Okay, so here think about is, so when we read papers, we're supposed to think about it, and also for Yufan. So when I think about Yufan, it's because Yufan is going to automatically combine or connect the 2 pieces of source code. So what can we do for connecting 2 pieces of source code? So in this case, I think the corpus is also very important. Not like Yihao's work. Yihao's work is the corpus is just there, and we just try different approach to achieve them. And for Yufan, giving 2 pieces of code, and how could we decompose them? So in this case, you still need to think about how to construct a corpus. So my idea is that we're using some heuristic to find a method. Usually a method should be a very good software engineering practice is that each function or each method should be responsible for only one responsibility, right? So that is practice. So whether we are able to think about just using some program analysis technique to know that this method actually combine 2 approach. For example, usually there's some work like there's a piece of code is going to prepare some things, another piece of code is going to prepare something else, and how could they be combined together? And also maybe we can find some features on the internet. For example, this kind of feature is to visit the database, the DBM systems, and this part of things is for rankings and whether they can be combined together. So in that case, we need to spend some time to think about it. And what is a combined version? So my idea is that to think in a reverse way. We first find some code which combine multiple functions. Then we decompose them into separate functions. And our model is going to learn the separate functions and to predict or generate a version of their combined code. So I think that might be the way to go to construct a corpus.
Yeah, I think so. I think we should use the reverse way. I think it's better.
Otherwise, it's very hard to build a ground truth, right? Yeah, and for Yihao, so in this case, the transformer will be very useful. I'm think about is that first, please go and find, because for program structure, so this paper or this work look into AST, right? But AST is just AST is useful for creating some code. But sometimes from a semantic point of view, sometimes I just feel the control flow graph. The control flow graph means that the if else or while. So this structure seems more important than the AST. And sometimes the data dependency, for example, the variable used before, the variable defined before, and it has been used later. So there will be more like, let me write some code there. So for example, there's the int a equals to 5. All right, so if b is greater than 2, then I will create c is greater plus a and b, else so a is equal to maybe 6, etc. Right? So in this case, we will have suppose 1, 2, 3, 4, 5. Suppose let's have 6. 6 is means that b equals a, something like that. So if we are building the control graph, suppose 1, 2, 3, 5, and finally 6. This is control graph, right? And for data graph, it's supposed to be C will be connected to A, and the 6 will be connected to 1. Of course, 3 and 6 is going to connect is going to connect to 1, right? So this graph is supposed to be provide more semantic meanings than the AST. So that's what I thought in my mind. To further improve the giving this transformer approach. But moreover, I think one of our selling point, or one of our novelty of our work is that we are looking to different source. So we have argument, we have empirical study showing that all existing translation-based approach are missing something. Specifically, we are missing 90% of the information used for comment generation, right? So in this case, we are going to bring up more structural information, and we definitely doing there's the multi-headed attention mechanisms. It's very easy to encode the self-attention, but how do we borrow the self-attention? So that'll be a problem. And also in meetings, or maybe you can investigate it. So your questions. So Yufan has already taken notes for your question, which we're going to address address later. You can, when you find the answers, you can just share it in the group, or you can just discuss this. We can discuss this in our next individual meetings. And for Yihao, so one of the questions for you that how self-attention can improve the model prediction or the model performance. For example, self-attention in images will definitely help to improve the face generation, because sometimes the relation between eye, nose, mouth, ear So these relations have to be kept by self-attention mechanisms. But how these transformer can benefit from the self-attention structures, so it is still unknown to us. But I think it's very, we can understand it there very soon. So please take notes, and if you got the answers, you share them in the group.
Okay.
Okay, but anyway, so the most important task for I think the most important task for Yihao, because you have a deadline in 9 to 6 weeks. So the most important thing is that to think about how to encode the context information into the model architecture so that it can outperform the rest.
Okay.
So that will be very important. Okay, so next time I will think about addressing the prepare the paper draft. I'll think about prepare the paper draft later. I will let you know when the template is ready, and if the template ready, then I'm going to draft something.
Okay.
And also maybe you can help me draft something before providing some materials.
Sure.
Okay, I think that's all, and I think there's a fairly long debate and discussions, and I hope for the next students, for students preparing next presentations, I hope that you try your best. For example, Yihao's presentation is very simple, but the logic is quite clear. It will not invite my questions. But Yihao, you're supposed to, of course, I understand, so maybe the time is limited, but I suppose that you can focus or provide more, put more attention about some basic information, so that we're not so many questions. And moreover, let's think about how to construct a corpus, and maybe the Codebert will be a useful information for us to use later.
Okay, I think the original paper is actually because all the mechanism is borrowed from other paper, like the BERT the mask language model and the replace the language model. So actually, I need to try to refer to other papers.
Yeah, but it's good for you to start reading those papers. It's good for you to start, right? So you need to equip yourself with a lot of knowledges. So then you have to you will be informative enough to make the right decisions in which direction to go.
Okay, thank you.
Okay, thanks everyone. Let's call it a day. Bye.
Bye.